All right, let's jump right in. You ever wonder how we know what's hidden right beneath our feet? It turns out we can use electrical signals to map things like caves or pockets of water. But sometimes what we find just creates an even bigger mystery. So today, we're going to solve a really fascinating underground puzzle where the signals seem to completely contradict themselves. So this is the central question, the thing that can really puzzle geophysicists. You've got two cavities under the ground. They could be sinkholes, caves, you name it, but when you measure them from the surface, one gives you a negative reading and the other gives you a positive one. How on earth is that possible? Let's dig in and figure it out. So scientists use this technique called self-potential, or SP for short, to look for these underground voids. It's all about measuring these tiny, naturally occurring electrical voltages in the earth. But like we just saw, the results can be super confusing. One hole is negative, the other is positive. Well, it turns out it all comes down to one key scientific principle. And that brings us to the hero of our story, the streaming potential effect. This is the fundamental idea that's going to unlock this entire puzzle for us. It might sound complicated, but trust me, the concept behind it is actually pretty elegant, and it explains everything perfectly. So what is it? Well, to put it simply, it's an electrical voltage that gets created whenever water moves through porous stuff, like rock or soil. And the key mechanism, the really important part, is that the water physically drags charged particles, specifically positive ions, along for the ride. So let's really break this down. First, you've got water flowing through the ground. As it moves, it acts kind of like a conveyor belt for these tiny positive ions. And that leads us to our simple golden rule. Wherever the water flows to, it carries positive charge with it, making that destination more electrically positive. Now remember that rule. It is everything. Okay, rule in hand, let's put it to the test. Let's open up our first case file, the empty, air-filled cavity. We're going to apply our streaming potential rule and see exactly what happens to the electrical signal we measure up at the surface. Think about it. An empty space underground is like pulling the plug in a giant bathtub. It's a zone of what we call high permeability. Thanks to gravity, it acts as a natural drain, sucking any nearby groundwater down into it. It's basically a sink for all the water in the area. So what does this do to our electrical signal? Well, as that groundwater gets pulled downward into the drain, our conveyor belt of water is carrying all those positive ions down and away from the surface where we're taking our measurements. So by removing all that positive charge from the area, it leaves behind a net deficit right at the surface. And that is how we get our first result. It's simple, right? You take away a bunch of positive charge. What are you left with? A relative negative. So, the surface directly above that empty cavity shows a negative electrical anomaly. Mystery number one, solved. Okay, so that explains the negative signal. But what about the other hole, the one that's giving us that confusing positive signal? Let's look at case number two, the cavity that's already filled up with water. We're going to use the exact same rule, but you'll see the outcome is completely different. Now this is a whole different ballgame. Unlike the empty drain, a water-filled pocket acts as a reservoir, or a trap. It's a dead end. Flowing groundwater can't just pass right through it. Instead, the water flow converges and basically hits a wall, forcing it to slow way down or even stop. So what happens when our conveyor belt of positive ions slams into this reservoir? Well, it creates a traffic jam. All that positive charge it was carrying gets stuck and starts to pile up right at the boundary of that water pocket. In some situations, the pressure might even cause a slow upward flow, pushing that positive charge even closer to the surface. And there you have it. This accumulation, this pile-up of positive ions, creates a surplus of positive charge right where we're measuring. The result? A clear, positive electrical anomaly. So the exact same principle gives us two totally opposite results, and it all just depends on what's inside that hole. Okay, we've looked at both sides of the coin. Now, let's bring it all together and put the final pieces of this polarity puzzle into place once and for all. So here it is, laid out, plain and simple. This table just explains the whole puzzle perfectly. On one side, the air-filled cavity acts as a drain. It pulls water and its positive charge down and away from the surface, which gives us a negative signal. On the other side, the water-filled cavity acts as a reservoir. It causes water and its positive charge to pile up and accumulate, giving us a positive signal. It's just a beautiful, clean cause and effect relationship. So the big takeaway, the secret to the whole thing is this. It was never really about the hole itself, was it? The signal's polarity, whether it's positive or negative, is determined entirely by the direction of the groundwater flow. Is the water carrying positive charge away from you, or is it bringing it towards you? That's the entire mystery solved. And that kind of leaves you wondering, right? We just saw how something as simple as water flowing through rock can generate measurable electric fields. It makes you think, what other invisible forces are constantly at work, shaping the dynamic, complex, and amazing world that's right under our feet?